you. And with the recording of the meeting, let me speak to the learning objectives and do so with regard to the course outline. So in the big picture, we have two components to the course. The first component is reinforced soil, mechanics-based analysis, a capacity demand that's very much a force moment, shear stress driven approach to design. And thus our material properties in lecture number 1 were those of strength, interface shear strength, and creep phenomena in terms of load, strain, time, and because of the thermoviscoelasticity of the materials, the polymeric materials, load, strain, time, temperature data. And the word durability appears at the tail end of lecture 1. There have been one or two, I'll call them passing comments on durability, but the first learning objective of today's lecture, lecture number 12, right down here at the bottom, is to capture in a concise and relative comparison approach durability of a sloped reinforced soil wall. It's actually durability observations and data for the Norwegian wall, number 1. And then through comparison, compare those observations to durability observations for a geotextile filter at a dam. That's durability case study number 2. And then durability case study number 3 is to look at experience with the durability of a geomembrane at a waste containment facility. And there's I'd almost call it 3 case studies of, if we look at it from the geosynthetics point of view, the good, the bad, well, let's call it the not so bad, the good, the not so bad, and the ugly. And let's view the case studies to fall into those categories. So that's the learning objective is to link the durability mentioned in passing in lecture number 1, which then led into lectures 2, 3, 4, 5, and 6 on mechanics-driven reinforced soil applications of various types with either live load dominating, witness lecture 2 and the resource access roads, or self-weight or dead weight load dominating, witness, for example, the slopes and the walls, and moving from a deformation reasonably tolerant scenario, lecture number 2 with the resource access roads, into deformation intolerant, as is the case for the retaining walls. So material properties 1 wrap into principles of analysis and design, number 1. And then we move to material properties number 2. And this is very much more a hydraulics driven, a pore size. In soil mechanics, when we talk of soils, we talk about pore size constrictions as well as the voids or the pore sizes. But pore size characteristics of geotextiles and geonets, I guess, arguably. The hydraulic properties, hydraulic conductivity in plane or cross plane. And then a passing comment again on durability, but really that's just a place marker to carry us through to the lecture 12. And from there, we followed to lectures number 8, 9, 10, and 11 from filters and drainage. I think it all comes together in barrier systems, but filters for suspended solids retention, possibly, but certainly filters for base soil retention in routine filter applications, filters around wick drains, the geonet drains, Darcian and non-Darcian flow in drains as an appreciator of the flow regime, and then into the barrier systems. So that's where we are in the big picture. And let me ask if there are any questions of clarification on that little overview of the course in advance of moving into a lecture on durability that will take up most but not all of the time this morning, with 3 case studies, and we'll break out into breakout rooms for the second of those 2 case studies. And then I'm going to revisit this same course outline to speak to the format of the final exam upcoming soon. But before we do that, please let me just check in with you. Are there any questions of clarification, any comments to be made? If so, please just unmute yourself and ask, and I'll pause momentarily. And there being none, very good. Let me then move on to the notes for today. So, as I mentioned, in the absence of my document camera not working properly, I'll be marking things up. So, durability of geosynthetics. Let's reflect on the geosynthetics themselves. The geosynthetics come in a variety of product styles or types, the geomembranes through to the geotextiles there, and a series of polymers that are used. And the polymers have different molecular structures. We won't dive into those, but that makes the difference between, for example, a high density polyethylene versus a polyethylene with a lower density. And there can be everything from linear low, very low materials that have been made, may not necessarily be made and sold at the moment, but a variety of densities of polyethylene, different polymeric structures that make the distinction between the polyethylene, polypropylene, PVC, polyesters. And it's not an exclusive list, especially with the geomembranes. There can be some, let's call them quite custom formulations, but polyethylene, polypropylene, PVC, and polyester are probably the most commonly encountered. And I think it'd be good to acknowledge that the polymer types, this one, which I'll capture it just with a little highlight to help us, not because I want to make anything special of it, but that's polyester.
Sorry to interrupt, but I don't think you're sharing your screen properly.
Oh, you are keeping me honest, and thank you very much indeed. How about that? Is that a little better?
Yeah.
Thank you. All right. I tell you, hanging in by the skin of my teeth here with that quasi-seniors moment. Thank you very much indeed there for keeping me honest. So I've highlighted this one not because it's particularly important, but because it's polyester by let's call it by its chemist's name. Now we see that the polymers are primarily the resin, and then we get some additives in there. Okay. The additives may be, in the case of PVC, plasticizers of various percentage. And can you imagine how that might explain the difference? Let me reach for PVC. Can you imagine how that makes the difference between this PVC geomembrane with its percentage plasticizer and a harder PVC pipe, for example? So there's the world of plasticizers. There may be fillers of various sorts added, primarily to assist with the with the kind of the processing of it, additives to assist with handling. Carbon black is a UV inhibitor. And then the catch-all phrase additives on the right-hand column there would speak to processing aids, little antioxidant, antioxidant packages that are put in to enhance durability. And the reason for that is that geosynthetics will tend to degrade and degrade more aggressively due to photooxidation, as well as elevated temperatures. And so the additives package, together with the carbon black, are the content that's introduced and will be extracted or leached over time more aggressively in UV light. Witness a geomembrane that's left exposed at elevated temperatures and with increased exposure to oxygen content. And thus, for example, that's why burying a geosynthetic will certainly tend to promote its durability, all things being equal, because of the absence of UV light and the greater reduction in prevailing oxygen in the environment around it. So we have those materials, and if I scroll on down, in a specification document, and I use this slide simply to set the scene for the case studies. The specification document will contain a number of clauses, general requirements, a certification and guarantee that you may ask the contractor to acquire from the manufacturer, certifications and guarantees as to the integrity of the product. For example, that geosynthetic, let's call it geotextile type A, manufactured by this company at this location, has these claimed material properties. And then there may be statements within the specification document for shipment and storage. How are the materials going to be stored in UV light or not in UV light prior to use in construction? Are they going to have a protective wrapping around them? When that protective wrapping is removed, are they to be stored off the ground and in the dry? Things like that. And let me just to give a tangible example of the resource sector, which tends to be a little bit more of the Wild West. But I recall looking at a yard of geotextiles being stored for use in forest road construction. The materials were excess to the previous year's construction season, and they were going to be used again. And the comment was, we will strip off the outer portion of the roll of the geotextile because we know it will degrade in UV light over the course of the winter. And recognize that, and so you'll write requirements for storage. The main reason for having this slide is for the sampling and testing, and that's where the text on the right hand side comes out there. You may ask at the time of sourcing the material, and in fact before it's delivered to site, you might ask, so at a designated period of time prior to construction, and I've done this, ask the contractors to submit the claimed properties of the material, perhaps accompanied by the certification or guarantee from the manufacturer. And you may ask for test results, and you may even ask for a sample of the proposed material itself. I have done this, for example, on larger projects where it's a choice for risk management, basically, that you don't get surprised by what gets delivered on site. So the source approval is a risk management approach. And then the conformance testing, you may want to have something like this, and we'll see the benefit of it for the case studies where you say, oh, and by the way, once the material is on site, I may be entitled to take samples and to check that the material that's delivered on site is indeed conforming with what was proposed for construction. In fact, let me encourage you to do this on jobs that you work with geosynthetics. You may actually cut out a coupon for yourself and archive it. And I wish I had done this more myself on projects, would be to archive samples of the material, because I have been amazed how many times I've wanted to go back and revisit actually the physical nature of the specimen. And you know, let me give you a very, very good example from British Columbia of archiving of a coupon of the material. The Tertsagi Dam, north of Lillooet, Tertsagi Dam, on which Tertsagi consulted, built in the 1960s, and it has PVC geomembrane in it as a part of the dam construction. And that PVC geomembrane was specified at the request of Tertsagi. He was in the latter stages of his specialist consulting career at that time. And a report was written on the materials at the time of construction. Coupons were cut out, including coupons of the seams and joins between the geomembrane panels. And that report with the historic coupons of the geosynthetic was archived and found its way to the Tertsagi Library. And it's held, the report is held in the Tertsagi Library at NGI. And BC Hydro had reason to go down and exhume go down and excavate down to the level of the geosynthetic a number of years ago, not because of the geosynthetic, but for other reasons, and took the opportunity to take a coupon of the geomembrane from the Tertsagi Dam at the time of those foundation works. And there was an opportunity then to compare the exhumed in the early 2000s with the coupon that was at NGI. So this capacity to acquire materials and archive them, let me impress that upon you. Now, I say that because now let's move into the case studies. And this is a stepping stone into those case studies. This is not one of the three, but I give you the HTTP URL there. And Bob Holtz, who lived in Sweden for a number of years in his early career, wrote up with Mike Harney a comparison of experience from an embankment. The embankment was in Sweden. The embankment was built with geotextile reinforcement sorry, let me scroll through here. And exhuming and comparing wide width tests of that geotextile. It was a woven geotextile. It was a woven polyester geotextile. The embankment was built in 1972. And so this would have been very early usage of geotextiles. And then samples were exhumed some 30 years later, and further wide width tests done on the exhumed samples. And I put this in here because the reduction in strength is considerable. It's of the order of about a factor of 2 or a little bit further. And it's unclear, just because of the nature of no testing being available on specimens that were exhumed at the time of construction. And let me just make this point because it's of relevance when we move forward to the three main case studies. You can install it, and then you could exhume at the time of construction specimens and test for construction damage or installation damage, if you see what I mean. We put the geosynthetic in. Let's take a geosynthetic here. We install it, we put the embankment on top. It's 1972, the year that ABBA was formed. And then you take some of the geotextile out at the time of construction, test it, and you would be able to test a, let's call it a brand new geotextile against a brand new geotextile, but installed and potentially it has experienced installation damage. Then we fast forward 30 years and you exhume more geotextile. And now if you test it, any further deterioration in strength, you can attribute it to a loss of strength over time that is over and above the loss of strength due to installation damage, if we view durability as being a time-dependent loss of strength. And thus, in this case, by inspection, the reduction in strength is of the order of a magnitude of 2, and that's because of installation damage and the 30 years of any degradation of the material properties of the polyester in the environment in which it's in. So that was my intent to include that. Now, again, with the passage of time, and let's go to the Norwegian structure. This is the structure that you analyzed in your first assignment. And we had opportunity through a project at UBC, Santiago Quinteros, a co-author here, Santiago, was doing his master's thesis at UBC. Santiago came up from Ecuador. And together with Suzanne Lacasse at NGI, we put together an industry university project with support from NGI. And Santiago went over to NGI to do plane strain testing of the backfill soil of the structure. And we also used the opportunity of his time in Norway and reconnecting with the Roads Authority, Roads Administration, to exhume some of the geogrid from that slope reinforced soil structure. And so this was some 25 years after construction. And a little bit like that Swedish case study, we did not, at the time of construction, 1987, the summer of 1987, we didn't put the tensor geogrid in and then pull some out just to see was there any construction related damage. So like the Swedish structure, after 25 years, any changes we're seeing we would attribute to installation damage and durability over the intervening 25-year period or so. The material, as you know, if we go in and capture that, it is an HDPE geogrid. It's actually Tensar SR55. Okay, and we did this knowing that there have been studies in the past. Let me draw your attention. For example, this, if I remember correctly, it was a US federal highway study by Victor Elias and co-authors, and they did a broad brush study. They I hope that doesn't do injustice to it. But they went to a number of sites and gathered data at 12 different sites. And those 12 different sites were largely from transportation, highways applications, burial periods of up to 20 years or so. And once again, no installation damage was previously investigated. Thus, we can't separate the serviceability, or let's call it the installation damage, and then the elapsed time. Maybe we can elevate our consideration of durability to be installation and the service life. However, by and large, they didn't see any evidence, no significant evidence of damage. But it was against that background of broad brush strokes that we went and exhumed the specimens from the Norwegian structure. This sets out the work. It was done in February, I remember, of a winter, hence that we have the snow on the structure in the background. It was when the roads administration, I guess, had a slow period, and thus the in-kind provision of equipment and labor was relatively easy for them to provide. So recall the structure has two sections, Section J and Section N. Section N, if you recall, has a series of 8 layers, and they're all the same length of reinforcement, 2.2 meters. And so we dug down and exhumed layers of the geogrid. The layer number, or the uppermost layer, number 8, a little bit of a sacrificial. That was a practice go to try and get that out without damaging it. But it took 2 practice goes to come up with a technique that actually worked. So the human story is we would have taken 8 and 7, but in fact it took a couple of goes to refine the use of the mechanical excavator, hand excavation, and train the crew so that exhuming the material didn't lead to any adverse damage. Because remember, we wanted to check for damage, but we didn't want to inadvertently damage it while we were taking it out of the ground. The ground was frozen as well, probably for about the first 20 centimeters into the structure. And thus we were working down from frozen ground and into unfrozen ground. And you can imagine the caution that ultimately you want to exert to expose the geogrid without, you're actually being quite careful towards the end and brushing it gently and cutting it carefully with a knife, all the while in the Norwegian winter. Nonetheless, we exhumed those layers and did a number of characterizations. Now, in the absence of actually physically testing the materials that we used in construction, and looking back, we never thought this thing would be sitting there for 25 years. So there was no intent originally to turn this into a long-term study. So that's why Table 1 has typical characteristics of Tensar SR55 geogrid. That's just from a manufacturer's brochure at that time. We couldn't even trace the Tensar that we used in construction back to a particular production run at the factory or a lot number. We had to rely on very generic numbers. Knowing what we know now and knowing the purpose of the 25-year study, of course, I would have done it differently at the beginning. So that's what we have for the product nominally as it would be supplied to the project. And then for layer number 3, 4, and 5, let me just go back up here. Layer 3, 4, and 5. Yes, 3, 4, and 5. 6, I'll speak to separately. So for layer 3, 4, and 5, then we went in and tested the materials and measured them. And you know, the bottom line here is that there's almost no evidence of any significant change. And where is the evidence that would be in support of that claim? In this QC ultimate tensile strength 57, 60.4. And remember, this is a nominal value, a characteristic value. This is the test value on the average of the test value on the exhumed layers. Peak strain 11.2, peak strain 12.6. I don't think we can read anything into the subtleties because our table 1 is so general. This is quite interesting, the carbon black content. Here's the minimum carbon black content, and it's met or exceeded as might be expected. The melt flow index is a little index test. It's related to crystallinity of the geosynthetic. That was we won't even attempt to compare it back, but it's just a number that suggests to the manufacturers there's been very little change. And then we check the geometry, no change in the geometry. There's a commentary over here, claims that are made from the evidence presented in table 1 and table 2. And the argument is, you know what, we see no difference. And that was independently corroborated because layer number 6 here was shipped off from Norway to Atlanta, Georgia, and we carried out isochronous load strain curve tests. Now, once again, we're relying on typical values for the original material. These would be the isochronous load strain curves, for example, that you looked at when you went through the first assignment. We didn't have custom, nor could we reasonably expect, custom isochronous load strain curves for the lot that was delivered to Norway and used in construction. That'd be crazy. But the manufacturer was sufficiently interested that they said, listen, we'll pay for new isochronous load strain time testing on your exhumed layers. Now, I thought it was layer number 6, but it looks like it was layer 3 and 5. I guess we must have mixed and matched between them, so I stand corrected there. And the manufacturer said, we can do that, it's that easy, we can do it in our labs. And I said to Mark Wayne at Tensar, I think it'll be more credible if you put a bit of budget into it and you have the isochronous load strain curves done at a third-party lab. I think the credibility, I'm sure you'll do as good, if not a better job, but the credibility of the process. And he said, I agree with you totally. So the isochronous load strain curves were obtained from an independent third-party testing lab to the manufacturer. And those are the circles, open and closed, for the exhumed layers. And I don't know about you, but I think if we look at those, the agreement is excellent. Not often that as engineers and geoscientists, we talk about excellent agreement, but I think that actually is. And we looked at the incremental strains. I won't give you the plots and the data here. They're in Santiago's thesis. But in terms of the load strain time behavior at a temperature of 20 degrees at 1 hour, 10, 100 hours, 1,000 hours, and 10,000 hours of creep loading, that actually was very, very encouraging. I look at that and say, after 25 years, not only is the geometry of the grid apparently as comparable to the original material, Not only is the quality control load strain testing, let's call that an index testing, but the careful controlled isochronous load strain curves are good too. So that's a rip-roaring success story. And why? Because do you remember there are these 3 case studies, and we're about to break for the middle one. But remember I said there's the good, there's the not so bad, and then there's the ugly. And let me throw it open to you guys. Why do you think that this type of construction offers opportunity for such good agreement? Why? What is it about this situation that gives the geosynthetic a pretty good chance of not degrading too much? So I'm going to stop sharing, and if anyone would like to offer an opinion, what is it about this Norwegian structure? What is it about the nature of the application? What is it about a reinforced soil slope or wall that in all likelihood it means that the geosynthetic is in a favorable environment and thus not necessarily vulnerable to terrible degradation?
I would like throw a guess that it's relatively dry compared to the other scenarios. There's no real movement on.
Yes, I would agree with you on that. Number one, the environment is dry, or let's use the word relatively dry. A little bit, you know, what I can't remember what the water content of the backfill soil was, but a moist to dry environment. Yep, there's one reason, and thank you for that, Grant. Any other thoughts as to why it might be that we see little or no evidence of degradation?
Potentially because they're covered and maybe sort of lower temperature environment in Norway?
Yes, I would agree with you on that. Relatively speaking, Ryan, the geosynthetic in a reinforced soil slope or wall is going to be covered relatively quickly, all things being equal. Let's say in comparison to, and let's go to a worst case scenario, a mine waste tailings facility in the Chilean Andes, and you're at elevation and you've got UV lights, you know, very, very strong. Hey, let's go to Bolivia and just make the UV light even worse, right? And let's say your geomembrane panel is installed and then it sits there for months, perhaps, maybe even a little bit longer before it's necessarily covered. Whereas at our structure in Norway, the geogrid is delivered and within days it's been cut and deployed. So Grant is correct that the soil is relatively dry. Ryan, you're correct that it's covered relatively quickly. Any other thoughts in terms of why a reinforced soil slope or wall is a relatively benign environment in terms of being favorable towards durability? There's a couple of other things, but they do get to be a little, I'll call it subtle.
There's no chemical process or bacteria growing there, so it was just a clean sand.
Yes, odds on that in terms of biochemical activity, the backfill of a slope or a wall is unlikely to have anything aggressive going on there. Quite correct. I think another one is that in comparison to many situations, the degree of engineering supervision during construction is probably relatively high, per unit volume of the structure compared to the extent, for example, of a waste containment facility. And there may well be engineering supervision at a waste containment facility, but you're maybe not watching everything that's being done all the time. On a retaining wall or a slope, there may be a chance that there's greater engineering supervision. Perhaps the compaction is a little bit better controlled, the compaction layers and the backfill material itself a little bit better controlled. So, and culturally, what I'd like to do is to park reinforced soil structures as being at the gentle end of the durability world for geosynthetics. And leave you with one other comment. I kind of liked it. I picked it up at a trade show once when a couple of contractors were talking, and they said, in many cases, installation, the day of installation is the worst day in the life of a geosynthetic, by and large, in structures such as slopes and walls. If you don't damage it during construction, odds on the service environment of a reinforced soil, slope or wall is not going to be particularly aggressive. All right, so we'll call that, and I'll go back to sharing my screen now that you've got me well trained. Let's move on from the good to the not so bad. Let's take a look at it, okay? So for this one, let's move. We're still in the 20 plus years. And this is Valcross Dam. It's actually an interesting dam. I've had the privilege of visiting it. It was designed and constructed by Giroux, and I was in contact with JP Giroux, and he was wonderful. I had an occasion, I was visiting friends in Europe, and I said, you know, I'm not going to be a million miles away from the Valcross Dam. I might just go and take a look at it. And he sent me maps, and he sent me Google Earth photos annotated, and he sent me the name of the contact in the local municipality. And long story short, I got a guided tour of Valcross Dam, which was a privilege. And Valcross Dam, that Philippe Delmas actually was the key mover. He's one of the co-authors here. The dam built in 1970, described by Giroux back at that time. We're talking the same decade of the building of that Swedish embankment dam, by the way, that Boggles was involved in documenting. It's not a trivial structure, 20 meters high, not particularly long, 140 meters long at the crest, and it was the first of its size in which geotextiles were used, and Giroux was quite the innovator and quite the driver. He was one of the founding principles of Geosyntec Inc. in the United States as a consulting company, for the record. I think he's retired and living in Florida now. French originally. And 2 geotextiles were used, okay? 300 grams per meter squared, non-woven, downstream. We'll look at where the downstream is very shortly. There. And a 400 grams per meter squared, non-woven, upstream here. In and around, underneath the riprap for the, nominally, the upstream slope protection. So let's carry upstream, and let's carry downstream where there was a drain, okay, and different geosynthetics used. I'm going to ask you to break out shortly, but I want to set the scene for the breakout, okay? So Philippe Delmas went in the 90s and sampled and actually wrote it up. So the write-up that Yves Foray, the first author here, the write-up here, they actually almost provide a synopsis of Philippe Delmas's findings. So Delmas went in 1992 and sampled the materials. And that was to complement work that had been done in 1976. So Valcross Dam has been the subject of several investigations. Specimens of the geosynthetic taken by Giroux himself in 1976, and then a second grabbing of coupons of the geotextile in 1992 and written up there. And that's where the 21 years is coming from, the 1970s construction and the 1992 program. Okay, so there's a description here of the sampling. There we go. Not inconsiderable works. Okay, here's the test pit. I'm not too sure what WorkSafe BC would say about people working in a 4-meter deep pit. And I don't think that the PPE in those days in France appears perhaps as it might be today. So let's acknowledge, and appropriately, what we would expect currently in health and safety. Notwithstanding that, the specimens were taken, and there's a drawing. This is the upstream face of the dam. And there's a drawing that shows where is the drawing? Do I have to go back? Bear with me. Yeah, figure 3. Let me go back, because there's a terminology that we need to pick up on, and it'll inform your breakout groups. So on the upstream face of the dam, let's say here's the water level. So the upstream face of the dam with its water level, there's our water level. Okay, there's the water level. And so we've got sampling on the lower strip, on the overlap, upper or lower part of the overlap, and then the upper strip. And that's on the upstream. Oops, that's on the upstream face. On the downstream, where these toe drains, there's the underside or bottom of this geotextile wrapped gravel. And then there's the top part, and it's the top part of the overlap versus the top part unoverlapped. So a number of sampling locations, and there'll be claims that follow from this. Remember, the upstream geotextile, 400 grams per meter squared, the downstream geotextile, a little lighter at 300 grams per meter squared. And then we have evidence in support of claims. Let's look at the evidence and then the claims. And I want to break this out into 3 groups. Yes, so let's look at the evidence here. So we have strength testing, table 1 and table 2 with strength testing. And the strength testing, we have specimens exhumed in 1976, specimens exhumed in 1992. And what are they going to be compared against? They're compared against specimens that were acquired in 1976, but had not been used in construction. That's what the little footnote means there. So once again, and it's you know, I'm in the same boat. We never archived materials at the time of construction. We didn't test materials at the time of construction. So it's exhumed 1976 compared against new material, happened to be acquired in 1976, and exhumed in 1992 compared. And there are data for strength, okay? Then there's a claim made with regard to the strength. And let me show you where that claim is. It's at the bottom here. The test results show no significant differences between the tensile characteristics observed in 1976, 1992, tables 1 and 2. Okay, there's a claim for strength. Let's go to the second of 3 claims. And that's to do with tables 3 and 4, not strength, but hydraulic. And there are data on permittivity and data on opening size. And those are for the 1992 in the downstream zone, that's table 3. And then if we go over the page, there's table 4, 1992 in the upstream zone. And information on permittivity and information on filtration opening size. Okay, and from those follow some claims. Okay, what are the claims? The claims are the hydraulic properties of the upstream, downstream geotextiles have remained unchanged after more than 20 years of use in the ground. Okay, so you know what I'm going to do? I'm going to create 3 breakout groups. Stop sharing this, and I'm going to generate 3 breakout rooms. They're going to generate automatically, and I'll give you 10 minutes, please, to go into those groups and can group number 1. Actually, you know what? I don't think it's going to, in 10 minutes, I think you can look at everything. Take a look at those 2 claims, the strength claim and the hydraulic claim, and see whether the folks in your group, you reach a consensus, and let's see if all the groups agree with that. So in room 1, room 2, and room 3, that's going to work quite nicely. I'm going to open those rooms. It's 10:55, and please come out at 11:05, okay? Thank you. My friend. And I want to take you and picking up where we left off. Let me share the screen, and I want to take you to this image first. So when we talk about you know, what's it looking like? This is an optical microscope image of one of the strands of the tensor grid. I'm not going to get too excited about a few scratches. We see them on geomembranes all the time. This is the rib of the geogrid, but very evident in geomembranes. And we saw just the occasional little encrusted grain of sand. It looks like iceberg scar in some kind of soft deltaic deposit in the something like that. But can you imagine, you know, and hey, you can't have interface friction without scratching, and you can't have interface friction without a little bit of gouging going on as well. And this is what we see. So it kind of gives us a physical sense. And remember, this is benign, this is non-trivial, made no difference to isochronous load strain curves. We're not going to get too excited about this. And here's an image of the fibers of the geotextile exhumed from Valcross Dam. And in their paper, they say, you know, we should try and understand this a little better. I thought one of the nice little complementary statements to inform our appreciation of what we're looking at is the scale is given by the diameter of the fibers. The fibers are 26 microns. So this is 26 microns, arguably. This is 26 microns. You can Google the original documents. I did it last night. And this is 26 microns. And so we're not going to put a geotextile into the ground and have water flow through it and so on without something going on. And you know, we ask ourselves, what is that something? If this is 26 microns, is this about a tenth? Is this 2.6 microns? Is this a little bit less than 2 microns? We're getting down to clay-sized materials, or is this some kind of precipitate? And no answers to those questions lay within the scope of it, but it just gives us a sense of what's happening over the surface life on the surface of the geosynthetic. I'm going to pick up now and return to the lecture and take us to the third case study. So we've gone from the good to the not so bad, and this one is the ugly, all right? And Kerry Rowe, our go-to guy in Canada for everything to do with waste containment facilities. And they had the opportunity to go in and look at a landfill liner after 14 years. And they put in place a framework for understanding what they were looking at. The framework is shown here, where they categorized where coupons were taken from. Relatively benign in an anchor trench to arguably quite aggressive below the leachate level where there was no sunlight, leachate, and let's call it sludge deposits. So we got, and they kind of give it this, no sunlight, no leachate, right? In fact, for many of you, and I say this slightly tongue-in-cheek, but I guess for many of you, you've not had much sunlight either, right? So in terms of your situation, you can probably identify with the no sunlight, no leachate. Then above the anchorage trend, or sorry, out here on the beach level, sunlight, no leachate, above the alternating leachate level, pond level. Sunlight and leachate, then we go underneath, no sunlight, leachate. And so that's, you see it, arguably, 1 is not as aggressive as 2, which is not as aggressive as 3, likewise to 4, 5 is the most aggressive. So we have a little categorization of things. And what does it look like? I put this in, but let's go to the original because it's a little bit more evident in the original. They talk about holes, they talk about cracks, and they talk about patches. And here holes, cracks, and patches. Yeah. So here's a evidence of cracking. Here's a seam, looks like a fillet seam, and it has cracked here. All right. So in their documentation, they then put together a little bit of a summary of what they saw, and this is a summary. It's a bit like the geometry of the grid in the Norwegian structure. This is the recording of cracks and where those were occurring. So we got what's happening here? We have cracks by their location, holes by their location, patches which are obviously repairs of defects, and And if you add up the 21 cracks that they observed, and if you add up the 7 holes they observed, and if you add up the 54 patches that were in there, 54 patches that were in there, you end up with a total number of defects, and you can look at it in terms of defects per hectare or defects per square meter. Interestingly, I highlight from their text, of the cracks, only one was located below the leachate level. And with that in mind, that table, the table 2, then leads to a summary of the 82, that's the 21 plus the 7 plus the 54, 82 cracks, holes, and patches, I'm quoting again from them, were observed in the geomembrane, an average of 582 defects per hectare over the 14-year period of operation. And there will be defects because of thermal induced stresses. There will be defects because of thermobiochemical induced stresses. There will be defects potentially because of construction damage that's partially patched. There will be defects because if you've tested seams or maybe done some coupon testing, you may have to patch that after. There can be many and varied reasons for patching, okay? I have been on a site for a geomembrane. I was a visitor. It wasn't a site that I was responsible for. I was a courtesy visitor. And the contractor brought out a roll of geomembrane, rolled it down a slope, and it had been punctured by the 2 forks of a forklift truck, right from its very outside to the very center, as if someone had thrown 2 javelins into it. And it unrolled like a series of perforations on a page of stamps. And the contractor just looked and said, well, that shouldn't happen. And the roll was taken off and scrapped. So all sorts of things can happen prior to, during shipment and storage and handling and placement and installation damage, and then the service life of the structure. Okay, we accept that. And we may not have the same kind of engineering supervision square meter by square meter as we get in a reinforced soil structure. So that's on the physical defects. What about on the state of the material itself? And again, no coupons from the original time. So just like Valcross and just like myself in Norway, you end up comparing to generalized values. But one thing of measuring the state of a material is the so-called OIT. There is an oxidative induction time. It's an ASTM test, and you put a sample of the geomembrane in a cylinder, and you elevate the temperature, then you introduce oxygen, and the the oxygen then starts to eat the antioxidant package. And once it's eaten its way through the antioxidant package, the geomembrane actually combusts. So you can measure the time, basically, that it takes in this little index test, the OIT test. We don't need to go into more details, but a long time, and typically modern geomembranes, as Kerry Rowe and co-authors observed, a modern geomembrane might have the order of about 100 minutes before you've, in this standardized test, consumed the antioxidant package. And in fact, the timing for the specimens here was of the order of 1 to 7 minutes. In other words, this OIT index test was saying, you know what? You've sampled geomembrane from the field, and almost all of the antioxidant durability package has been consumed already after these 14 years. or quoting from Kerry Rowe, the OIT of 1.8 minutes in this SNL location, and indeed the others of several minutes, is pretty much close to an unstabilized HDPE. So we have a geomembrane with a lot of holes in it. We have a geomembrane that its antioxidant package has been largely consumed, varying a little bit by location. And if we look at the strengths, the yield strength was higher than typical modern geomembranes, while the strains at yield were lower. Remember, there can't be a like-for-like comparison, so it's kind of, this is what we measured, and here's a generic expectation, implying the geomembrane is stiffer than would be expected for a modern material. And all of that is what led Kerry Rowe. We're not looking at the clay liner, but they looked at the geochemistry of the clay, because this geomembrane, if we go back, I don't know if I made this comment. Let me go back to the abstract. We don't have to go that far back to get to the abstract. The geomembrane is a geomembrane against a compacted clay. It's a composite liner. If you remember back to our previous lecture, it's a geomembrane placed in direct contact with an underlying compacted clay. And in their paper, they look at the geochemistry of the compacted clay. Now, if we go forwards, we've only looked at the geomembrane and its durability. Now if we go forwards, and Kerry Rowe is the absolute master of evidence-based claims. He is a consummate professional when it comes to documenting things. So the summary and conclusions. We've got this 1.5 millimeter HDPE. It's been in this leachate lagoon, leachate pond level, varying over 14 years. The number of defects, here we're getting into the evidence. The number of defects, right, coupled with the geochemistry of the chloride profile in the clay, suggests that the geomembrane likely did not perform its design function for very long. So the holes are allowing for advection of leachate into the clay, and in fact it was the clay that acted as the liner. The geomembrane, not so much. Then the amount of antioxidant, or let's say the remnants of the antioxidant package, the additives package in the geomembrane, measured. And how is it measured? Using the standard test method, OIT. There's a variation on that, but we won't go into that detail. But the amount of the antioxidant measured, right, generally less than 7 minutes, indicates that the antioxidants were almost completely consumed for the exposed part of the geomembrane. Okay, and thus with that we can expect a change in the tensile strength, and if we couple that with the now he says here low values measured, the yield strength embrittled, but the tensile break properties were actually lower than expected. So the yield strengths were higher, it was stiffer to yield, and then the break values were lower than normal geomembrane strength. So that's where that little comment comes in for tensile break, not tensile yield. If we carry that on through, We talked about that OIT. I didn't really talk about stress cracking resistance, and that's a little bit of a dark art in some respects. Right. Show that the geomembrane ceased to effectively perform its barrier function at a relatively short time after installation. Right. However, because there was the presence of the compacted clay in this composite liner, the chloride had only diffused about halfway through the clay layer, and therefore the failure of the geomembrane as a component in a system, the failure of the geomembrane did not cause any adverse impact on groundwater. And this is amongst, we don't know anything about the temperature. Maybe I could go back and haul through for the temperature of the leachate. But in contrast to the reinforced soil structure, this is a very aggressive working environment for the geomembrane. It's exposed for 14 years to the elements. It has an alternating pond level of leachate. And who knows exactly what the time series of holes and cracks, development in the patches and so on. But the combination of leaking through holes and the combination of the degradation of the membrane, perhaps the stiffness or embrittling contributing to some of the cracks, especially in and around wells. This is, I think, a very nice example of the kind of things that can really challenge in an aggressive environment. And heck, you sure wouldn't want to be relying on the geomembrane alone. The presence of the composite system actually was very good. In fact, you might turn it around and say, why bother with the geomembrane at all? And I remember the words, Kerry Rowe wrote a very nice book, Clay Barrier Systems, with a guy called Robert Quigley. And I remember giving Bob Quigley a ride to a VGS meeting, I kid you not, 25 years ago. Bob Quigley passed away a number of years ago. And I was chatting with him just in the car on the drive it was when the VGS meetings were downtown, tells you how long ago that was. And we were chatting, and Bob Quigley said, you know, we got an awful lot of clay in Ontario. We really don't need that. We really don't, there's not a big call for geomembranes. And I said, so under what circumstances, Bob, would you even consider the merits of a geomembrane? And he said, you know, if I had a material and it was aggressive, and the service life of my barrier was very long, and I was importing clay and placing and compacting the clay liner, and it was an aggressive waste, I think there's good reason to put a geomembrane in, because even if the geomembrane component of the system doesn't last for the whole service life of the structure, it gives the clay barrier, which has been placed and compacted, time to consolidate and to mitigate construction joints within the clay, and the geomembrane will allow the clay to get into the best condition to do its job over the full service life. And I would capture what he said as the geomembrane is an auxiliary to the clay barrier. And I kind of wonder if there's, you know, you look for connections in this world, and, you know, the South Africans arguing that maybe a geotextile is an adjunct to a granular filter if you are looking to manage risk. And maybe the concept of a geomembrane as an adjunct to a clay barrier in some situations, and that you needn't necessarily, depending on the components of your system, not every component has to have the same service life for the system to perform. And there's an interesting philosophical point on which to draw a closure on issues of durability. And were I to wrap it back up with embankments, probably a geosynthetic doesn't have to be an embankment for more than about 3 or 4 years. And any contribution that it would make to the stability of the embankment is done as the strength of the embankment gains with time, the strength of the embankment foundations, right? So let's not mix up service life of a system with the required service life of components in a system, while still ensuring that durability and service life are adequate for all of the components in the system. All right, so enough of philosophy 579, if not philosophy 101. But I didn't want durability to be a discussion driven by test methods and driven by chemistry of polymers and chain scission of UV light. I wanted durability, I wanted to influence the way you think about durability and to put you in a position where you could ask the right questions or go looking and interpret evidence-based claims. Now, back up to the course. So here are the learning objectives of the course. I'm going to make a couple of closing comments and then I'm happy to entertain questions, okay? So the learning objectives of the course were understandings of material properties and how they're obtained and how they correlate with material observed and performance monitoring data. And then an appreciation for uncertainty and development of nourishing an element of judgment. And then an ability to interpret through constructive review the implications of research findings for innovative design practice. And maybe some of the case studies we've looked at in durability would speak to that a little bit. And as I said in my opening comments, it's a course of 2 halves. There's the first half, which is largely a mechanics-driven, force and moment equilibrium driven design of different types of deformation tolerant structures. And then the second half is one of hydraulics, drainage, filters, applications. The durability is spoken to both of them. And so we run in now to the design, to the last part of the deliverable. Oh, you know what? Maybe I should still share my screen because let me remind you, apologies, let me remind you that the final exam is an open book final exam and its contribution to the overall grade. And let me pick up on this open book examination, Friday the 11th. And my thoughts are as follows, and they build largely on how I've examined 579 over the years. It has always been an open book exam. Generally speaking, I've given people the exam and asked them to go away and work on it and then give it back to me. On occasion, I've had people sit in an exam room, and on occasion, I've had an oral exam rather than a written exam. And it's just been a one-on-one question period. And out of that, the final evaluation was made. But my inclination this year is the following, that the final exam is open book. It would have 2 questions. One question would be more on a front half of the course, the reinforced soil, and the second question would be on the second half of the course, the world of filters, drainage. Were you to be sitting in an exam room, or were you to sit down and write your answer to the question, I wouldn't expect that it would take much more than half an hour to 45 minutes to write down what would be your submission. For the first question on the reinforced soil, and half an hour to 45 minutes to actually write down and document for the second one. Neither of them would be lengthy submissions, but I recognize it takes time to read a question, and then if you've got to go off and read some additional materials, as you know, either you go back and check some things in your notes, or maybe I've given you an extract from a report, or I've given you some evidence-based claims, and I ask you, just as we were doing today, what do you think of them? So I recognize that it takes a little while to read and familiarize yourself with the material. So the following is my inclination, but I floated out there for a little bit of feedback from you guys. My inclination is to release the exam on the morning of Friday the 11th and ask you, for example, 9 o'clock, and ask you to give it back to me on or before 5 o'clock that day. My inclination is not to say give it back to me the next day, because it's just not worth the pain and suffering of having it in your possession for any longer than you need to. I would be devastated if you worked on it non-stop from 9 in the morning to 5 at night. I would feel that that was an abuse of the Geneva Convention on Human Rights. I'd like to hope that you would spend an hour or thereabouts familiarizing yourself with what you've read, and let's say another hour documenting it with a factor of safety, 2 hours, 2 questions, 4 hours. Let's throw another little partial factor of safety in there, 5 hours, half a day. Half a day of effort. But my inclination is to say, listen, why don't I give it to you at 9 o'clock in the morning and you give it back at 5? And then I think to myself, yes, but if someone's sitting in Africa or someone's sitting in Iran, what time is 9 in the morning and what Vancouver, and what time is 5 in the afternoon Vancouver? So I haven't quite puzzled that bit out, right? But I'm asking you to do it in that time. So I might release it at 9 in the morning, equivalent to someone in Iran. They can work from 9 to 5. I might release at 9. So maybe the time zone that you're in, I'll release it at 9 o'clock in your time zone and ask for it back at the end of your day, wherever you are in the world. And all I ask is, please, it's your own work you're handing in, and you know that's fine. I'll just ask you to enclose a little statement that says, I haven't misbehaved like the people in the math department at UBC in their midterm ne'er-do-wells that they are, and I trust you. So I'm not worried. Okay, I'm not worried. So that's where I've got to. Any comments or observations? Synopsis, open book, 2 questions, 1 on the front half, 1 on the back half. each of them requiring a little bit of reading and synthesis of information, looking at evidence, and then I either ask you to make claims or evaluate the claims of others.
I have a question. In terms of releasing the exam, is that going to be done on Canvas, or is it going to be done by email, or do you know what method that's going to be completed on?
That's a good question. You know what I might do? Because of the time zone issue, and it's uncharted territory for me, I think what I'd probably do is email it to everyone individually. And then that also offers the email link to return it to me and solves that, where do I upload it to, or how do I get it back to you? Right?
Okay, great.
Now, if anyone has, I'll call it a constructive refinement to that, hey, let me know. But that strikes me as probably the simplest way to do it. Yeah, and I can do that online from a class list, no problems.
And following up on that, would you like the submission like a handwritten and scanned or typed up, or?
Handwritten is fine, and handwritten and scanned, or if someone doesn't have access to a scanner, and I got to hold my hand up. I got a scanner 2 days ago when someone gave me a scanner and said, hey, I've got two. So you could take pictures of it and send them in as JPEG pictures if that's the technology that you have available to you. You're probably much smarter, and you can scan off your iPhones and all this sort of thing, just like my youngest son. But a PDF or JPEG images, handwritten or typed up. I'm more interested in the thinking and the opinions and your ability to express them, rather than the finished look of it. Don't run around formatting things forever and changing font sizes and searching around for a UBC logo, etc., etc. I'm really interested in a little scan of your brain rather than a scan of a beautifully formatted document. Any other questions?
So one kind of geosynthetic we didn't discuss in this course was grout socks. I was wondering if you had any experience with grout socks.
No, I haven't. And there's another, I thought you were going to say geosynthetic clay liners, or GCLs, which is another one that I haven't really spent much time at all on. Let's call it a fancy cross-stitched geotextile with a bunch of bentonite or some similar product in there. And no, there's a number of exotic species and semi-exotic species that, depending where you are in the world, maybe you use them more often than less often. But I've focused primarily on the materials that I've had direct experience of, and I would say, hopefully, knowing what you know from what you've covered, you have a solid base to be able to deal with other materials that are part of, this is going to sound terrible, but the geosynthetics family. Anything that's part of the geosynthetics family that we haven't covered, that you would be able to bring some of the principles here to bear on them, Taryn. Yeah. And likewise, I promise not to spring a final exam question on grout socks upon you either.
Thanks.
Yeah, you're welcome. Without wanting to be too cryptic, I think you'll have seen already the materials that you'll be asked to read or familiarize yourself with. You'll have seen them in one shape or form already. I'm not going to wander too far from home base on this, okay? We'll keep this reasonable.
Will we get the grades for our previous assignments back before the
Yeah.
exam?
Yes, you know, that's the sword of Damocles that's been hanging over my head. And yes, I feel morally obliged as well as professionally obliged to get your assignments back to you. The assignments you would get back will be the design assignment number 1 and number 2, and then you get the commentary back on the discussion exercises, but not marked up versions of the discussion exercises. I feel that because we talk about those in the lectures, that we cover off on the relevant bits there. But your reinforced soil assignment and your filter design assignment, those will be returned to you. I guess I'll mark them up and then scan them and return them to you. And I should do that. I should do that in a couple of days in advance of the final exam. Does that address that question, Amy, or any other follow-up aspects that you wanted to chase?
No, it just would be good to know where we kind of stood in the course grades-wise before we went into the final.
Yeah, that's right. I think at the moment you've got grades for 1 discussion exercise out of 3 and 0 homework assignments out of 2. So currently it's pretty slim pickings. I hear you, Amy. And sorry, and just to clarify, Amy, you will have the 3 discussion exercises and the 2 homework assignment grades before you go into the final exam.
Perfect, thanks.
Yeah, there we go. There's the moral contract recorded. Any other questions, you folks? Okay. Well, listen, I appreciate that sometimes questions can come to mind, and I appreciate that you may want to follow up on something. What I might do is when I put in writing, as I will do today about the final exam, I'll indicate an hour that I'll certainly be available should anyone want to contact me, you know, a sort of an office hour. I know it's a curious concept when people are in different time zones, but also if anyone has you know, you just have a question, pop it to me by email. I'll probably set up a Zoom call because to explain it in words is a little easier than trying to write a lengthy response to a question. But if there's anything that you do have questions of clarification on, please pop them my way, and I'll endeavor to fix up a time to chit chat with you about them. Okay. What's your next week looking like, you folks? How many, are there other exams next week? What's the general culture across the courses that you're taking in terms of final exams? Am I the only one with a written exam next week, or are some of my colleagues also engaging with you in a similar way?
We got soil mechanics on Monday, and then there is other exams on that same week.
Right. No. No, believe me, I don't envy you. Let's put it like this. Very good. Listen, I'm going to wrap things up here now. I wish you well in the days ahead, and do look after yourselves. Take your physical and mental health seriously, and also those of friends and colleagues around you. I wish you well. Don't sweat bullets over the CIVL 579 final exam, please. It's worth 15% of the course. It's not a huge component of the course. And as I said, when you come to read the materials on the exam, you'll be familiar with publications that I'll be drawing it from. Okay, so it's nothing's going to come at you from left field. I can assure you that I'm not a big fan of trick questions. I've never been a fan of deriving equations. I really just want to make sure you're not a danger to society. And if you can show me you're not a danger to society, then we're all good. Okay. At this point, I'm going to stop recording it.